So the other thing we'll be looking at for our operators is the set difference. So if we take two relations R and S, we have an output of AB with our alpha of 1 and our B of 1. What we're going to be looking at is the set difference between these two relations. So set difference operation tries to find tuples that are in one relation, but not the other. This is kind of R minus S. Defined as for the set difference between two relations R and S, find all the tuples such that each tuple in R and the tuple is not in S. Okay, so that's kind of how it would be in English. Set differences must be taken between compatible relations. So R and S must have the same arity, so essentially the same number of attributes as we said earlier. The attribute names of R and S must be compatible. So union compatible is similar to that idea. So the same things apply for our union, but we're just looking at things that aren't in one but are in the other. Okay. When do we want to do this? Same type of idea. Courses that are taught in the fall but not in the spring 2010 semester, we could say for my first one, select semester fall and years equal to 2009 for my relationship section and project the course ID and take the set difference from this relationship and set difference between the relationship of selection of semester spring and years 2010 from the relations section and project that course ID from that outcome. So if I subtract these two together, it looks like a minus sign. We'll get CS347 and Philosophy 101. CS 101 was taught both in the fall and the spring. So we're only going to take the 347 and the Philosophy 101. Okay. Our next one is the Cartesian product, which is all the it looks like a multiplication between them, but essentially it outputs all possible products that we can get by the combination of two unions here. So again, I have my relationship R with A and B, and I have my relationship S with C, D, E. I get a new relationship here where I get all the attributes together, and I get A1 with A10A, A1 with B10A, A1 with B20B, A1 with Y10B, okay? And I do the same for my next row. So for each row of my one relationship I'm multiplying by, I take it to each of these ones here, right? I don't know if the cursor is obvious, but I do row 1 times row 1, row 1 times row 2, and so forth, okay? And again, it's useful to remember that your location of where you put these two informations is useful, right? So sometimes when you do the set differences, it might be different based on which one you're calling for it there sometimes. Cool. So the Cartesian product combines any two relations, computing all combinations of tuples. R by S is going to be defined as the Cartesian product of relation R and relation S is equal to all the tuples in both of them, such that T is in all relation R and all the relations, and all the tuples are also in relation S. So definition here might be a little more confusing than what is actually given for us here, but just think of it that all of them are going to be combined as the output. Nothing is different, but you will most likely get a new relationship from this Cartesian product. This assumes that attributes of R and S are disjoint from each other, and if attributes in R and S are not disjoint, then renaming must be used, which is one of the later selection operations that we have to look at later on for us. So for a quick example we have of Cartesian products, we'll see here that my instructor ID, my teacher ID is selected here, but we notice here a little bit that my artery might be a little bit off. So we could see that my attributes are a little different, but for Cartesian product, it's not too bad of an issue because we don't really care about having the exact same amount here, because we could see here we get a new relationship that has much more attributes than our previous two. Noticeable is the renaming here. You'll see this when you actually code. What happens is if we have the same the same attribute name, is that it will say relationship.attribute name. So essentially, if my relationship is instructor and my ID, is ID, I will have instructor.id for one attribute and then teaches.id for the other attribute. Okay. Most likely this will be the same here for some of them, but you can see here when we get lower down, they change up a little bit. So from our composition of operations, we could say relation R with the Cartesian product of relation S is what gave us this one here. So we're going to ask what is the RA expression that we have here. And we could say from this output, I'll show it here, we could say select the predicate A is equal to C for the Cartesian product of R by S. So select for the relationship from the Cartesian product of R by S, which is this big guy, where A is equal to C. And this is where A is equal to C here. So we get the first one down. A is equal to C here with B2, B10A, B2, B10A. A is equal to C beneath that one, B2, B20B. Okay, so we get tree products outcome there. So again, you can do the composition of operations not with just like a project into a selection, but you could also do project into a selection into a Cartesian product type of deal as well. So it can get very complex, but essentially this is the basis of our query languages. Cool. So this was a bit of a few examples. It might be a little choppy because I spliced together. My computer's a little glitchy there, and I wanted to make sure that my explanations weren't too convoluted. But essentially, you covered your unary and binary expressions for your operations there. There's one more we'll look at briefly called the rename one as well. But in general, if you feel pretty comfortable with each of these and what they're supposed to do, you'll be good to go for the SQL coding of when we do it. And don't worry about like having to code calculus. We won't do that. But I just wanted everyone to know what's actually going on with the logic behind when we actually type SQL code.